Perfecto. Me gustaría muchísimo hacer esta lección en inglés, en español, pero no creo que voy a conseguir, entonces va a ser en inglés. So voy a speak in English now, okay? Thank you very much to all the organizers. For me, it's special. I mean, it's fantastic that they organize this activity. It's really, I think that they represent the greatest possible success of what the ICTP diploma could lead to. So I'm extremely happy. Yes, go back. Yes, so the title of the presentation of the class is Evolution and Ecology. I switch ecology and evolution. And before I start, one very important thing. Please ask questions. Right? If there is something you don't understand, it's very likely that the other, I don't know, 70% of the people in the room, they're also not understanding. So please ask questions whenever there is some doubts. I mean, I don't have to, I tend to run toward, thank you. I tend to run on what I explain. So your goal is to slow me down, okay? To make me go slower and to ask as many questions as possible. Okay? The other things, as Kavi said, I mean, I think this is an occasion also to discuss a lot as much as possible. So this time, if you have questions, please ask them as much as you can, or if there is something you want to discuss or whatever. Okay, so the topic that we are dealing with is going to be evolution and ecology. But before I start with that, I'd like to.
Okay, could you try that?
Okay. Doesn't work. Is this two on the? I would think so.
But maybe first you need to.
Yeah, to connect this.
Yes.
Physical theory.
Okay. Yes. Okay.
Okay.
And you cannot do this.
Okay. Yes. Perfect. So before I start, I want to spend one word about where I'm from and what I do. So I'm from ICTP in Trieste, and actually I sort of thought before how my story is also very much linked with Guatemala, because I was hired literally by Fernando Quevedo, and Fernando Quevedo was the one that created the section of quantitative life sciences, without which I would not be here. So it's fantastic that there is all these things of returning, and of course, we have this diploma. I think we will have occasion to talk about, and as I said, like the organizers, Joshua, Carlos, and Mani, are like an example of people that went to this diploma, and so I think really. I don't know, the number of people from Guatemala in Trieste probably is like much higher than what expected by chance. And in my life, in my scientific life, what I do are like problems related to ecology, evolution, especially in microbial populations. This is the sort of the plan for this week that we're going to be together. So this is divided in 5 slots. It's okay if you don't arrive to the end. We can also stop here for 5 days. It's totally fine. But this is sort of the plan that what we're going to do. And so it's sort of divided roughly in 3 parts. Today is about exponential growth. Then we're going to talk a bit about evolution, and then more about ecology. Okay. Just to have a sense of sort of what is your background. So, who come from physics? Okay. The other that don't come from physics come from biochemistry, biochemistry and biotechnology. Okay. And so, how many of you ever heard about? Ever studied evolution? Okay. How many people ever studied lot count and equations? Okay. How many people have a background in calculus? Probability. Now, yeah, now everyone. Okay, good. Just to have a sense. So again, I will discuss about stuff. If there is something that is unclear, the notation, please interrupt me. Okay. Okay, so a lot of the material of this, I mean, is going to be shared with the fantastic organizers, but you can also find in here, there are notes. So all the math that we're going to do is more or less there. From this slide, it seems that I might be organized. I'm very disorganized, so also these notes are partially disorganized. It's very much stream of consciousness in some sense, but there should be everything that I'm in the class. Inside here, there is also a link to some collab notebooks. How many people are able to code in Python? Python. How many people code in another language? What? I mean, how many people? How many people don't code in Python but code in another language? Okay. How many people never coded? Okay. So this is some code that sort of try to follow what I do. I will not during the class use the code. I will use the output of the code, but the idea to share this with you is that you can play around. So the idea is play around as much as possible. Disclaimer: all this code was AI generated, which means that we are in 2025. But also means that, these are sort of powerful tools, and as every powerful tools, use it with responsibility and care. So, I use it because I knew what I wanted to have at the end. So the code produced the right result, okay, the correct results. Use these things also to play with it, but remember this disclaimer, okay, in your life. Okay, so today, first part, exponential growth. Okay, so what is exponential growth? Exponential growth is a phenomenon that is very common in many fields and is very common also if you look at us. So this is the plot of since we're going to talk about evolution, how many individuals of the species Homo sapiens lived on Earth from 10,000 BC to today. Okay? And what's striking about this plot is, of course, that for 8,000 years, there have been less than 200 million people on Earth, right? And in the last 10 years, we increased of 1 billion. Okay? So what's striking about exponential growth is the speed and how fast it goes. Okay? This is another things that you might remember, the good old times of COVID. So this is actually, joking, but it's not joking. This is the number of deaths in the UK because of COVID. And what you see is that something is very flat, and then it starts increasing dramatically. Right? And so if you remember those old days, you could have experienced with your life what it meant, right? That you knew no one that had COVID, then someone had COVID, and then everyone had COVID. Okay? And this was very fast. And this is just because in the initial phase, things tend to grow exponentially. Okay? And so today is about this thing. Okay? And what is going to come next is what processes actually change or disrupt exponential growth. Okay? If you want, ecology is all about why things are not exponential. Okay? So what I want to start from is to describe very simply what and why we have exponential growth. And then I'm going to talk variations, where include stochasticity and exponential growth. It's okay if you leave the slide. I wanted to try to write here. Is it better than writing here? It's the same. It's better. My plan worked. I'm very happy. Now it's a success. I can go. Okay. So let's say that.
Sorry, can we get 2 minutes to
Yes.
show? Could you share double screens?
Okay. Do you want me to stay silent or?
No, I mean you can.
Or I can, no, we can go on, or maybe should I tell a joke?
Oh no, maybe yes. For 2 minutes?
No scientific content.
No scientific content.
Okay.
So could
Joke?
you mute?
My son has this book of jokes which are very stupid, like made up all the time.
Okay. Okay. Yes. Okay. Let's. Thank you.
No, sí, bueno. No tengo mucho tiempo. Ah, pero ahora como lo veo.
Es que tenemos que darle clic a eso para
Ajá.
que funcione.
Okay. Ahora sí, probar con.
Pero creo que si vos
Ok.
clic a la cosa activa, funciona.
Si tienes que hacerlo.
Ah,
Ya.
okay, so let's try to write together the goal that we have now is to think about the population. You can think about the human population. You can think about I don't know, the trees that are outside us. You can think about bacteria that grow in a colony. And we want to write the simplest possible model to describe their growth. Okay? So the simplest possible model that describes this growth is that there is no growth. Okay? So let's assume that there is some growth. Okay? So why the population change over time? What are the fundamental processes that make the number of individuals to change over time? Reproduction? Death. Good. Okay, so let's imagine that for simplicity, we forget about the fact that usually people reproduce with others. Imagine that we reproduce asexually. Okay, so you are one individual and you can produce another individual. Okay, So there are two fundamental processes, we say. There is birth and death. Okay? So it means that if we have a population n, no,
Oh.
what happened? It's
I wanted to touch it. Why did it go wrong?
That's okay.
It was this one.
Yeah.
Ah, okay.
Okay.
That's good.
That's okay. So we have two processes, n going to n plus 1, or n going to n minus 1. Okay? So this is birth, and this is death. Okay? Now, what we want to describe quantitatively, it's how this happens. Okay? So, what is the simplest possible scenario? The simplest possible scenario is where our n individuals, they are completely independent of each other. Okay? So if we imagine to want to describe how frequently one individual reproduces, okay, we can quantify, introduce a constant, a quantity that defines how likely is that an individual reproduce per unit of time, okay? Or how much time does it take between for an individual to reproduce, okay? So let's call this quantity B, which somehow represents how frequent an individual reproduces, and then we have death, okay? So this B is the rate, okay, at which individuals reproduce, which means that if I take one individual and I look it in a given time delta t, the probability that it reproduces is d times delta t. And the same for death, right? So we all have a death rate, right? So I can ask what is the probability that we die in the next second. Okay, now, no one died, but there is a probability that some of us die in the next second, right? Production is more complicated, but that is possible, right? Because then these things fall on my head, and then so this is like at the individual level, okay? So this is, let's say, this is a rate, okay? And so these together, it's a probability. Okay? Now this is for one individual, okay? Now we have n individuals, okay? So how do we have to modify? So what is the probability that we have this event here? What do you think is this probability? So every individual has a probability d times delta t of reproducing. Okay. What is the probability that one individual reproduces? This is a tricky question. But let's say that we are in a very simple setting where it's very, very unlikely that this event occurs. Okay. So it's very, very unlikely that one of us dies in the next second. Okay. But if there is n of us, and we assume that more or less these are independent, how many events do you expect to see? I don't know. I can add more prompt, right? So imagine that you are in a place and there is a probability that one individual reproduces, okay, in a given unit of time. And now you consider another place and there is another probability that this individual reproduces. There is another place, there is another individual, and there are n of these places with one individual each. Right? So you have n individuals, and there is this probability that one reproduces. Okay. How many events do you expect to see?
Maybe the number of people times the rate.
Exactly. So it's this times n. Okay. It's something a bit tricky that I realized while I was talking, but this is like the expected number of events that you have if you have n individuals. Okay. So basically, this is what is the probability that I will go from n to n plus 1? Okay? And this is the probability that I will go from n to n minus 1. okay, in a short, a small delta t. The idea here is that this delta t, in which I sort of describing the system, is very, very small. That's why I talked about 1 second. So at most, there is one event. Okay. Now, I want to describe how the population changes over this time. So what I want to say is, what is going to be the population at times t plus delta t? Okay. So what is going to be the population in the next second in this room? Assuming that no one is. Okay? How do we describe? Well, first of all, we have to know where we start from. And then?
Plus b delta t n minus t.
Plus b delta t n of t
Minus or t, sorry.
Okay? So basically, the population 1 second from now is going to be the population now plus the number of individuals that, the probability that an individual reproduced minus the one that died. Okay? Good. So now what do we do with this expression? What do you think I'm going to do next? What is the next equation?
Divide in delta t to have the differential.
Yes, when you have something with delta t, what you do is that you take this minus this one and you divide by delta t, and you take the limit of delta t is equal to 0. So I'm going to take the limit of delta t going to 0 of n t plus delta t minus n of t over delta t, because this is equal to nice, many people ask. Yes. This is the derivative of n t, and this is equal to what? Okay? Is equal to what is on the left side, or on the right side, which is b minus d times n. Okay? So if we take this equation, what do we want to do with an equation like this?
Solve it.
Yes, so we want to solve it. What is the solution of this equation? Who knows? Yes. Of course, the solution of this equation is n of t equal n of 0 b minus b. So it's an exponential, where this quantity here, r, is what is called the growth rate. Okay. So what did we understood with this? What we understood is that if you take the simplest possible model of a population growth, so a population where there is some rate that individual give birth, some dates that individual die, okay, and these rates are independent. So the rate per individual, sometimes it's called the per capita rate, is independent of how many individuals there are. Right? Every individual has a rate, a birth rate b, and this does not independ whether there is 2 other individuals, 3 other individuals, there is another, I don't know, there are predators, there are resources, there are stuff. It's completely independent, completely static. What we get is exponential growth. Okay? So exponential growth is like sort of the inertial motion in physics. Okay? If nothing changes, a population will grow exponentially. Okay? That's okay. Okay. Now this is very general. So we saw this in this case where we imagine that this process is continuous and sort of each individual has a probability to reproduce at a given time. But this is fully general and is true also in other contexts. For instance, if you imagine that a population a population reproduced in other ways. Before I move to that, I want to say one thing because there is space here. So of course, what this solution look like? So this solution looks like something like this. So this is n versus time, and looks like something like this, provided that, under what condition?
B minus B.
Yes, that b is larger than b. Okay? On the other end, it looks like something like this. If the data rate is larger than the birth. Okay? Good. Question now. I'm going too slow, I'm going too fast, I'm going too medium. I'm going too fast? No. Is okay? Are you falling asleep? No. Good. Thank you. Okay. Yes.
Yeah, I was getting, since that B and D are the two exclusive events, there must be, they don't sum up to one, right?
Well, because these are probability per unit time, yes.
Yeah.
There is another probability, which is the boring event, what is happening now since I started the lecture, which is that n goes to n, and this happens with probability 1 minus d plus b delta t times n. Okay?
That doesn't change the math downstream.
No, because, I mean, no, it doesn't change the math. Because here, I mean, the only thing we track is changes, right? So what, I mean, in some sense, yes, it's this event is self-defined, right? If you, I mean, if you want to go the next step and say, okay, there are rates, then you could also say there is a rate at which the population stays the same, but it's like the same. Okay, good. Okay, so is this clear? So basically, this is like what we saw. This is exponential growth is the simplest things that you can have in equation. Now, you can sort of define exponential growth in another setting, which is more relevant. For instance, when population reproduces sort of discretely, so at typical times. Because here what we are describing is a case where as soon as you are born, you can reproduce. Okay? Which not always happens in all the organisms. Okay, so another case that we can imagine is that we can have population that reproduce discretely. So for instance, we can say that we have one individual, okay, and then this individual can produce some k individuals, can reproduce with k individuals, and this take some time td. Okay, so we can imagine that we have a process like this, and in this case, how do we expect the population to grow? Okay, so imagine that you have this event, and then these others produce other k individuals, etc. Okay, so what we want to describe is, imagine that you have this process, okay, how this process unfolds, what is going to be the population after some time. This is a question for you. Okay, so suggestion, the first point is that instead of measuring times in unit of time, it's better to measure times in unit of generations. Okay? This is a model where it says there are no overlapping generations, means that somehow you, well, this is not beautiful, but no, forget it. But since reproduction, of course, at definite times, it's better to measure times as generations. So I can say I have generation 0, then I have generation 1, then generation 2, etc. Okay, yes?
The weighted dies in.
I'm neglecting that.
Oh,
Okay? Here I'm neglecting that. You can add it. Okay? Exercise. Add that to this. Okay? So how will the population grow in this case? Okay? So what we can say is that we can look at the population at a time equal some TB times the number of generations. Okay? So we look at a time corresponding to, so if we look at generations, this is 1, 2, etc. If we look at time, we have TB, where we have 0, TB, to D, etc. Okay. So how is going to be the population after generation if we start from N0 individuals? How is going to be? How many individuals? So let's say that we have that.
A to the N.
Okay, you get the answer. It will be K to the G. Okay. So we start from 1. After 1 step, we have K individuals. After 2 steps, we have each of the K individuals produce K individuals. So we have K times K. Then each of the K times K individuals produce K individuals. So we have K times K times K. Wrong. Okay. Now we have this process here, and of course, in this process, you can recognize exponential growth. Okay. If you do some little math, what you can recognize is that you can write this G as D over D. Okay. And so this is N0 K D over D. And this one, you can write it as the exponential of D over dD log K. Okay? So what we discover is that also in this case, we can write these in the same form as we wrote earlier, and this corresponds to a growth rate which is 1 over dD log K. Do you have a question? No, you were, sorry, because you were like, okay. So basically, what is the growth rate in this case? What is the interpretation of the growth rate in this case? The interpretation is that it's something that is inversely related to the duplication time, so to the reproduction time, how much time it takes to reproduce. Okay, the shorter is the time, the faster the population grows, and it depends on how many individuals reproduce. Okay? For instance, if you like the world of microorganisms, like me, like Manny, and others, then usually this case is 2, because 1 individual makes 2 individuals. Okay, so usually that is log 2 over TD. Okay, so the growth rate is log 2 over TD, and in this case, TD, that's why there is a T, is the duplication time. How much time it takes to die. Okay, so this seems pretty clear, I mean, I hope, and actually pretty boring. I mean, because there is, it's like the inertial motion in physics, it's pretty boring. But there are some interesting consequences of these things, of exponential growth. So one interesting consequence is that exponential growth is very fast. Okay, it's very rapid. And so there is one interesting problem that you can ask yourself, which is the following. Which is, suppose that you have an exponential growing population. Okay. I mean, exponential growth is the thing is that it's pretty intuitive why it happens, but our mind is not tuned to deal with exponential process. Okay, so we live in a very linear mindset, and so everything that is exponential has sort of counterintuitive consequences. And so I want to present one. Actually, I will present 3, but this is like for this simple deterministic process. Actually, the title of the slide is wrong. It's okay, but this is deterministic. Okay. It's okay. Oh. Okay, thank you. So this is back to the one. It's fine. It doesn't matter. The title is wrong. Okay. So the consequence, the question I want to ask is: suppose that you have an exponentially growing population, and you can ask how many people or how many individuals are alive today, okay, respect to all the individuals that ever lived. Okay. So Now, in the process that I described this before, I said something stupid. I said that there is no death, but actually what you can imagine is that you reproduce and die. So you can imagine that you are one, and then you make k offspring and you die. Okay? So, because I need this now. Okay? So imagine that we live in this world where there are these model where there are these sort of non-overlapping generation. That's true. So there is a set of individuals, then they die and produce k other individuals before dying, and then so on and so forth. So generations are discrete. So the question that we can ask is, how many people are alive today? Well, the number of people alive today, so now, is simply the initial population, which we assume is 1, times k to the number of generations now. Okay? And then we can ask how many people ever lived. Okay? So what is the number of people that ever lived? Let's call this n top. Okay? So how many people ever lived? How do I count this? I integrate. In this case, I imagine that these are non-overlapping generations, so I sum. Okay? So there are discrete generations. So instead of integrating, I sum over generation. So I have this fantastic symbol, which is a sum. Okay? And then I sum from generation 0 to generation g. Okay, so I'm summing over all generations, the population at that generation. Okay? So I sum all the generations. I sum the number of individuals here, the number of individuals here, the number, yes?
I think it's HT.
Thank you. Okay? I sum individuals here, 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 up to now. Okay? And so this is the sum from 0 to g. Again, I assume that there was one individual at the beginning. This is k. Okay? Good. How do you do this series here? Of course, you go to ChatGPT and ask. No, this series is called geometric series, and I mean, you can find the explanation. You can have ChatGPT explain it for you, or Gemini, or whatever you use, or you can go on Wikipedia and find the proof. But this sum here is something that gives k to the g minus 1 over k minus 1. Okay? So what you can ask is then okay. What you can ask is what fraction of individuals of the ones that ever lived is alive today. That will be n now over n top. Okay? And so n now is k to the g, and this one is k to the g minus 1 times k minus 1. So this was wrong, of course. This is k plus 1. Okay? Okay? Now, if you take this expression here, and you imagine that the number of generations is very large, okay? What do? If you take the number of generations that is very large, what are the terms that dominate? So this minus 1 does not count, okay? So what you get is that k over 1 divided by k. Okay? So this quantity here, you can follow the math of the notes. So, but the important point is if this quantity measures how many individuals of the ones that ever lived are alive today, and the answer is k minus 1 over k. So if you think about bacteria, yeast, things that duplicate, okay, k is equal to 2. Okay? So what we get is, for k equal to 2, we get 1/2. Okay? So this means that if you have a population growing, right, and this population grows exponentially, if you see the number of individuals that are alive today, it's half of the individuals that ever lived. Which is sort of surprising. And can you move this slide? No,
but
because this is
go
wrong.
back, right?
Yes. Go.
This one?
Yes, how do I?
I'm guessing it should work now.
Yes. So the point is, this is a sort of simple exercise that you can try to play. Is you can ask the same question for humans. Okay. So you can ask the same question for humans. So our species appeared around 200,000 years ago. Okay, and has not been growing exponentially. Actually, the growth rate of the human population is very interesting. Was very low. Then modern medicine arrived, and people stopped dying because of diseases, or birth mortality was very low. So I mean, this is, I mean, when you ask why science is useful, this is the things. So this is like the birth rates peaked around after the Second World War. Now they are declining. But in general, you can ask the same question for the human population. So if you imagine, if you ask of all the humans that ever lived, right, from the Maya culture living here many centuries ago, many thousands years ago, for, I mean, people living in I don't know, wherever, in all the history of humanity on Earth, how many humans are actually alive today? Now the answer, I will not give you the number. You can play. You can try to do different calculation. There are like subtleties. There are data, records that are very good now, that are very bad, of course, in the past. You can find the data here. There is one calculation that is reported in the notes, but you can play with this. But the surprising answer that emerged from the calculation we did before is that this answer is not going to be 0.0001%. Okay? What we discovered earlier is that a finite fraction of the humans that ever populated our world are alive today. Okay? Which sort of also explain why we have this feeling of the fact that everything accelerates. Right? If the, I don't know, advancement of technology, science, culture comes from how many individuals you have around, right? Basically, we have now a good fraction of the people that ever populated it, okay? Which is a sort of interesting and surprising result to me. Okay? Good. So this is what I wanted to say about the sort of simplest possible version of the model, which is like fully deterministic. At what time do we have to stop? No.
We have time, so lunch is at 12:30.
Okay, 12:30.
Okay.
Okay.
We can take a little bit more.
No, it's fine. Okay, no, just to know. I don't have anything. I mean, we can continue. Okay. Okay, so this is like the simplest possible model you can imagine, where everything is deterministic. There is nothing random. Now, I want to talk about other two cases of exponential growth, where there is randomness involved. Okay, so if you can you move to the next one? Okay, so if you think about how we introduce the process, the first things we discussed was about a model, and I discussed about probabilities. Right? So then I sort of forgot about this probability and completely, describe something where everything is deterministic, meaning that the model that we describe is a differential equation that we can solve, and if we start from the same initial condition, we will always get the same result. Okay? Are you here? Good. So now let's start again from the model we defined before. Okay. Now this process, of course, written in this way, is an intrinsically probabilistic process. Okay? So it's a process where if you and you simulate this model independently, for instance, you expect to have different results, okay? Because you take, for instance, what you can imagine to do is that you start with one individual, and then you ask, in the next second, did any individual reproduce or die? Yes, no. If yes, I add one individual or remove one, and so forth, and so on and so forth. And this is intrinsically probabilistic, right? So it's like tossing coins and see if individual reproduce or not, right? The reason why we use probability is what Harry described, that, of course, the processes that lead to an individual dying or reproducing, it's like very complicated, and probability is a very powerful method to capture this complexity, okay? And we can talk about the philosophy of this for years. But we have this process here, and this process is intrinsically probabilistic. Okay? So the correct way to describe this process is not to describe how many individuals there are at any given time, but we want to describe something else, which is since it's probabilistic, can we say anything about what can we say about the number of individuals 1 year from now? Their probability. Okay. So the object we want to study is not how many individuals there are, but what we want to study is what is the probability that there are any individuals at time t. Okay. And of course, when we study this problem, in the same way as we studied this problem with some initial condition, okay, when we study this problem, we want to study a problem with some initial condition, so some probability at the initial step, which can be, I use this notation, for instance, which or n0, okay, where this thing here is saying that basically this probability is equal to 1 if the number of individuals were exactly equal to n0. Okay? We have this kind of process, this kind of problem. So the question that we want to ask is, if we start with n0 individuals, how many individuals there will be in the future? Okay? Good. Now, how do we go in solving this problem? What we have to do is we have to write one equation that describes the change of this probability. In the same way as here we describe the change in the population, here we have to describe the change in the probability. So what we want to do is to have an equation that describes how this probability changes. And this notation for the not initiated one is just the derivative of this probability over time. So it's saying how the probability at the time t plus delta t minus the probability at the time n t divided by delta t. Okay? So it's the change of this probability. Okay? So how do we go and find this equation? Okay? Well, we can do the same things that we did here. And what we can say is that we can say, what is the probability of observing n individuals at the time t plus delta t? Now you tell me, what is this probability? Well, first of all, is the probability that I had n individuals at time t. Right? So if nothing happens, this is the baseline. Okay? So if the birth rate is 0, the death rate is 0, no individuals die, no individuals give birth, then the probability should not change. Okay? Now, how can this probability change? This probability can change in two ways. Because an individual gives birth or an individual dies. Okay? So let's consider, for instance, birth or death. Okay. Right? So what are the events that can change this probability? So in what way, so imagine that you have n individuals today, okay? In what ways you can arrive to have n individuals today? If you are looking in the past, where did you have to be in the past? How many individuals did you need to have in the past to have n individuals today? n minus 1, so you could have n minus 1, and then there was one of these individual giving birth, or you had n plus 1 and one individual died. Okay? So what we have is that we have to count here. So there is going to be plus something with the probability that there were n plus 1 individuals, okay, times the probability that one of these n plus 1 individuals died, which is d n plus 1 delta t. Okay? And then we have the same for the number of the individuals that give birth. So we have plus d n minus 1 delta t p n minus 1 t. Okay? Is that all, or there is something else? Do you think this is all? Who will find this probability, this thing here problematic? There is one fundamental reason why you could find this problematic. One reason you could find this problematic is that in this way probability cannot increase. Right? Because you have something positive plus something positive plus something positive. Right? So it means that you are missing something. How can the probability of being in a given state decrease? Well, you can decrease if you are in n and then you have a birth event or a death event. Right? So the probability of being in n decreases if you were in n and then one individual died. And then if you are in n and one individual gave birth. Okay. So if you do this, we have this equation that now that we obtained that captures all the possible steps. Okay. Now from this equation here, well, we can simply do the same things that we did before, and then we get an equation for this probability. So which looks like n plus 1, p of n plus 1 t plus b n minus 1 of n minus 1 t. Okay. Which this equation here is called master equation. Okay. And as everything that you have to deal with a process that is stochastic, you cannot write equations for the variables, but you can always write equations for probabilities, right? So the object that you want to study that has a deterministic evolution in some sense that you can consistently track is the probability. Okay. Okay. So so this is the basic structure of the problem. Then I'll stop here. So then we can have lunch. But what we're going to do next is not going to, there are a lot of calculations that you can do here, but what we're going to go next is to look at what happens if you simulate this process. Okay? So in the code that is provided, there is a code to simulate this process. And you're going to see, if you simulate one trajectory, so if you have deterministic growth, you see something like this. Okay? If you have this process, what happens? Okay? So suppose that you have deterministic growth. This is E b minus b times t. Suppose that you start with some number of individuals and you simulate this process once. What kind of trajectories do you see? Okay? Say that you look at once, twice, 3 times, so on and so forth. Okay? And the outcome is that there are going to be some surprises. Okay? Good. So before we have our lunch, questions?
Maybe I have one question. So here we have the probability dependent not only of n, but to n plus 1. So we have like sort of like the next
Yes.
is that like the next state influencing the one that is
Yes.
that is previously known.
Yes, so this equation here, so of course the probability of having n individuals depends on what is the probability that you also have n minus 1 in the previous time step, or n plus 1.
Previously, and
Yes, exactly. And mathematically is what makes this equation non-trivial. Right? If this equation was depending only on n, then it would be trivial. This equation here, I mean, in the notes there are, I mean, in this case, this equation can be solved exactly with some tricks. You don't solve this equation, you solve another equation, and all the calculations are in the notes. And for those of you who are interested in these things, you can look at it. But the point is that it's not immediate how to solve this equation,
right?
because it's not a nice piece to this equation here, because you have a partial derivative, and here's something that depends on discrete differences.
Just because it looks like the one that we had before, but with those two additional terms that are the influences of the n plus 1 and n minus 1.
Yes, I mean,
It's
what
like
you
the
have,
same, but with
what you have, if you want, this is a good exercise that you can do during lunch. Is you can take this equation here, okay, for those of you that like these things, and take this equation and say, from this equation here, what I can calculate is, I can calculate what is, I use this notation, the average n, okay, which is the expected number of individuals at some time. Right? And then this quantity here is the sum n equal to 0 to infinity of p and t times n. Okay? For those of you that sort of understand where this comes from, okay, for those of you that will not understand, I think you will see something similar in Harry's class, so you will understand. So you have this definition, this is a definition of the mean, and then using this equation here, you can define what is the derivative of this quantity, because the derivative of this quantity is the sum from n to infinity of n dp dt. There are no mathematicians, so I can exchange derivatives with series and everyone is happy, but this is what you can, I mean, in this case, you can do it safely. So you can write this equation here, right? And what you discover is that you can write this derivative as function of this sum, you substitute it here, and here you will get expressions that depends on the other. Okay? Good. But the point is that this equation is not easy to solve in general. In this case, can be exactly solved. In the notes, there is a way to solve it. But it's what is important for the message that I want to give is not how you solve this equation, etc. But is the fact that in this case, even if the process is stochastic, there are probabilities. I mean, everything depends on the realization. You have a mathematical framework to get consistent result on what's happening. Okay.